Okay. Good morning, everyone. So, not many are there anyway. We can continue. So, I hope I'm audible.
Yes, sir.
Hmm. Okay. So, we have already studied a few concepts. So let me share my screen. Okay. So now at this stage, uh, so I hope you. So are you comfortable with the idea of illegal intersection which we discussed in the last class? Or yeah, what's an illegal intersection? Can anyone tell me? Hmm? You don't know or what?
Sir, when in the transition cube, we implement it using two more uh, cu- with OR gates in with multiple OR gates, and it causes a problem in the form of static hazards or dynamic hazards. It's called an illegal.
No, I think we need to be a little more clear about that. See, this is where we explained the idea of an illegal intersection. Maybe I can open that earlier. Yeah, so let's see if, yeah, we talked, yeah, this is where we talked about. So here we had,
Sir, are you sharing your screen?
yeah, it is, it is
Sharon, I think your screen is not shared yet.
not shared, but I thought it was shared. Let me just check. Oh, okay, I think,
Now it
I,
is shared.
yeah, I hadn't completed the steps. Yeah, okay, yeah, all right. So, so if you look at this example, we have given a Carnot map where the four mean terms are shown, and we are considering the transition indicated by that arrow. crimson arrow. So it looks like a straightforward matter, but there is a subtle problem there. So the problem is as follows. Here you have this. This in this particular implementation, you have got three cubes: C1, C2, and C3, as shown over here, and the function is implemented as, you know, this is the function which is implemented. Now, these are the ideal waveforms of C1, C2. So, by the way, these are the mean terms that we are considering. Okay. So, the transition is happening from M1 to M2. Okay. The transition is happening from M1 to M2. But it's a multi-bit transition. All right. It's a multi-bit transition. Or I can say multiple input change. So it actually goes through this. And then it comes here. All right. So this is happening for a small period of time. This is happening over a very small period of time, as we mentioned in the last class. So I hope this much is okay with you. There is no problem with this, I hope. All right. So these are the ideal waveforms of C1, C2, and C3. So as you can see, C2 and C3 are these are monotonic. Okay, C3 is this is C3. C3 is going from 1 to 0. C2 is also going from 1 to 0. C3 C3 is 0 for this condition M dash. So, all right. So C2 becomes 0 only when we reach. This is C2. So it becomes 0 only when we reach M2. But C1 plays a fleeting role. It momentarily goes high and then goes low. Now the problem is that this is such a short time span, and if C1 has a slow implementation, then this could happen in this form. So this is where you get the you have a glitch. Okay, this is where you have a glitch, which was probably this is where you have a glitch. All right, so it was high, it goes low momentarily, goes high, and again goes low. So this gives you a dynamic hazard. Okay. Yeah, so that is explained over here. There's a dynamic hazard. This is the dynamic hazard, which is explained here. So So are you okay with the dynamic hazard? Do you understand this dynamic hazard which is happening? Yeah?
Yes, sir.
Hello? So,
Yes, sir.
yeah. So we don't want this dynamic hazard. All right. How could we avoid the dynamic hazard? Why is it happening? So it is happening really because of this, this non-monotonic transition from C1. So this part, which is shown over here, okay, this part is called an illegal intersection, okay. So this is the part which is giving rise to this glitch, and this one, if this glitch is delayed, it shows up as a dynamic. If this happens within this period, it's all right, but it could be it could be delayed to the extent that this rising edge crosses, it happens after these have fallen. So these C2 and C3 might be faster gates. C1 could somehow be a slower gate. So this is possible. So we don't want this. All right, this illegal intersection. So what we could do is we could cartel. We could cartel this part. So that is shown over here. All right, that is shown over here. Of course, I mean this. One thing you can see is that you do have another problem here. That means if you consider this 1-1 transition from, you know, uh, if you consider the 1-1 transition from A bar B C bar D to A bar B C D, that is a situation where you would actually like to have that cube, the C1 cube. So what you can see is that you could have inconsistent requirements, unsatisfiable requirements. On one hand, you want it to be carted, and on the other hand, you might like it to be there. So this um, problem of uh, problem of hazard-free design is not always satisfiable. Okay, you might have situations where you can't really achieve hazard-free design. Yeah. So anyway, so the idea of an illegal intersection. This is the idea of an illegal intersection. So um, you might like to prune some cubes so that you don't have this kind of illegal intersection. All right. So now let us see how we can go about it. Okay, so this privileged cube is, the transition cube for dynamic transition cube for a dynamic transition. That's a privileged cube. It's not shown here. It's this cube. All right, so how can we attempt two-level hazard-free logic minimization? So we consider, so assume this cube M1, M2 is a transition cube corresponding to a function hazard-free transition from M1 to M2 for some Boolean function f. And you are given an implementation which is C. It's a cube cover for f. So as you have seen, 0, 0 transition is all right. 1, 1 transition, we have seen that is free of logic hazards for inputs changing from M1 to M2 if and only if the transition cube is included in C. All right. So that's a requirement for 1, 1 transition. And if you have a 1, 0 transition, as we have seen that the privileged cube should be free of illegal intersections. All right. So let us see how we can go over. So we have the concept of a dynamic hazard-free prime implicant. So a dynamic hazard-free prime implicant is just prime implicant which may have been pruned to avoid illegal intersections. Those are dynamic hazard-free prime implicants. So the steps are as follows. That is, you want to generate all the DHF prime implicants. So first of all, you generate all the prime implicants, which you already know how to do. And then you reduce those to DHF prime implicants. That you do by removing those illegal intersections. And you might have some things, so after you have pruned, you might have some things left over which are redundant. Anyway, even if you keep those, it doesn't matter because the covering mechanism will get rid of those anyway. And then you want, so for this one-on transitions, you want to have some, you want to cover some of this required cubes. Okay, you want to cover some required cubes. So you have to cover those required cubes also. Okay, so those will also have to be covered in addition to the mean terms of the expression. So note that this required cubes also cover mean terms. So you don't need to cover mean terms which are covered by the required cubes as such. All right. So here is an example. We are considering some transitions. So we are considering 4 function hazard-free transitions. All right. So here, let us consider the transitions one by one. So this is the first. This is let us say the first transition. So what is so can you say what kind of a cube this is? This cube in red. What kind of a cube this is? Yeah. Can anyone try to? Can anyone try to tell what kind of a cube this is? Yeah. So first of all, it's a 1 to 0 transition, right? So this is a privileged cube for this transition. Now we have got so this implementation for this implementation we have well, these are the required cubes. So when you consider this, you want to consider the cubes which are, so you had a open transition cube. So this cube less this cell. So these are the required cubes arising from this transition. Okay. This is a one-on transitions. This is the required cube. All right. Then here you have I think this one is a bit misleading. It is, I think, from this one to this one. Yeah. So it's a, oh no, it is showing the whole thing. I think there might be a little mistake here. I think it should be just still here. Anyway, so these are the required cubes here, okay? We'll see. I think there might be some flaws. So these are the required cubes. And for this dynamic transitions, the starting points are shown over here. So these starting points are shown to, because we only want to keep cubes which include the starting point, because if you remember this situation where we removed the illegal transition, so this was an illegal transition. Why? It was an illegal transition because it did not include the starting point. That is why we had this glitch over here. This glitch is because the starting point is not included. If the starting point had been included, we would not have this glitch. So we want to remove, so all the cubes which intersect the transition cubes of this transition or the privileged cube of this transition, but doesn't include the starting point. Those are the cubes which have an illegal transition. So these are the starting points. So now you try to do a Carnot map reduction and let us see what we get. So this is one of the bigger cubes that you want to have, right? This is one of the bigger cubes. And this is okay. It doesn't foul with this because it doesn't have an illegal intersection because it includes the starting point. All right. it includes the starting point. So this cube you can keep. So it's marked with a tick. Then here is another cube. So for both these dynamic transitions, these cubes include the starting point. Okay. So these cubes are all right. You can keep these cubes as well. Looking at this cube, this also includes the starting point of this privileged cube. Okay, so this is all right. Then this one is all right. This has nothing to do with this dynamic, with this privileged cubes. So here is another one. This one also includes the starting point, so we don't have a problem with this. Let us look at this. Let us look at this. So this one requires further examination because over here, if you look at this here, it has an illegal intersection. A bar B C bar D. This is the illegal intersection. So we need to examine this further. If you consider this cube, this one also has an issue. Over here, you have an illegal intersection. All right, so let us examine this part. So the illegal intersection is shown over here. This is the illegal intersection. So let us prune this out. So if you prune this out, this cube is broken down into two parts. Okay. Now this horizontal cube, this cube is BCD. Okay, BCD. So BCD is okay because this one includes the starting point. So that can be retained. Okay. Now let us look at this. So this one again has an illegal intersection. This one has an illegal intersection shown in red. So we prune this out. So this is what you are left with. Okay. This is what you are left with. Now this one can be discarded. Why? Because it is already covered by other cubes which were considered. For example, this cube. So even if you retain this, this will get eliminated. Okay. This will get eliminated. And then, yeah, so this one is eliminated. So then this is what you are left with. All right, so let us consider that other cube. So this is the other cube. So here we have a problem. So these are the illegal intersections. So you can leave this out. So this is what you are left with. Now this is also redundant because this is included within that first cube which you had considered. So you can discard this as redundant. Okay. So after this, you have this DHF. So what is left after this? Those are the DHF prime implicants, and these are the cubes that you need to cover. Okay, and this is and then corresponding to this. Well, here you have some essential ones, and so these are two possible implementations that you can have: hazard-free hazard-free two-level minimized SOPs. All right. So this is the basic mechanism. That means, and it, as I've told you, in some cases it may not be satisfiable. Okay. So, um, do you understand the steps? Yeah. Hello. Do you have any questions regarding the steps? There are only a few of you in the class, so I think you can respond.
Sir, I think we need to practice a bit to get a habit of this.
Yeah. Yeah, so the important part is to, so you can try on this itself. I mean, you can identify the reduction. Yeah, you can consider you can consider the reduction. Uh, yeah, over here I think. I mean, I think this one might be a little big. It would be enough to consider this cube. This one seems to be a little big. Yeah. So I think yeah, this arrow was probably not drawn very correctly. I think it should be from here to here. Okay. All right. So you can. Yeah, so this one transition, you need to include the required cube. The required cubes need to be covered, and so there are two basic steps. You have to cover the required cubes, and the prime implicants need to be pruned to cut out the illegal intersections. These are the two steps. So, so, uh, so it's similar to the logic optimization. So earlier, what you were doing is you were covering just the mean terms with the prime implicants. Here, so let me just write down. Plain logic optimization. Okay, so here you basically have, you know, generate. So you have got two steps. All right, and you have cover, minimal cover of the mean terms using the PIs. So I think there is no problem regarding plain two-level logic optimization. I hope this part should be very clear to you, right? So now we are looking at hazard-free. All right, so here, this step is the same. So we first keep this. All right, so this step remains the same. Then what do we do? All right, so this is an additional step. You are um, you're pruning some of these prime implicants. Now note that or you can say all right. So, and just to, illegal intersection happens when the intersected region Doesn't contain the starting term. Okay, that is when you have an illegal intersection. And the thing is, well, let me put it in this. Yeah, required cubes. Required cubes should all be covered. And you can say um, alright, so all mean terms have to be covered anyway. So these are the steps for two-level hazard-free two-level logic optimization. So are you okay with this? Do you have any questions, any doubts regarding these steps? Yeah?
Sir, can you please show the steps once again on some other function? It would be helpful, sir.
Well, I don't have another. I'll have to prepare an example there. I don't have it with me just now. But these are the steps actually. See, generating all these prime implicants, you know already. Then you consider those, uh, dynamic 1-0 transitions, which are of course function hazard free, because if there's a function hazard, there is nothing you can do about the implementation. So you consider dynamic 1-0 transitions that are free of function hazards. So there, of course, first of all, you get the privileged cubes. Privileged cubes you have already seen the definition of privileged cube for a dynamic transition. So that's the this is the open transition, which is defined as this transition cube minus this two. So all these are the privileged cubes. All right. And then you also have also this should be covered. By the DHF prime implicants. Okay. Now, of course, you have to get the DHF prime implicants. So, DHF prime implicants are just obtained by pruning the prime implicants in case they have illegal intersections with a privileged cube of a dynamic 1-0 transit, and that we have already we have already seen. We have already seen what these are. So if the intersection doesn't include the starting point, that's when you have an illegal intersection. So illegal intersections have to be removed. So once you remove the illegal intersection, you are left with pruned prime implicants, which are the DHF prime implicants. Then you just got to cover the required cubes and any mean term that may not be included in the required cubes with the DHF prime implicants. So that is it. Yeah, so it is always good to, yeah, I don't have another example right now. I'll have to create one if you want to see another example.
But I think the steps are clear. I mean, if we follow these steps, it can always be done.
All right. So I don't know whether maybe I can include some examples. I'll try to include some examples. All right. So any more questions? All right, then I think we can close this topic here. Yeah. Okay. Pavitra, I think.
Yeah, maybe we can start the next topic.
I'll stop sharing my screen. Yeah.
Okay. Okay, so what we want to cover next is that you have studied all these combinatorial circuit and sequential circuits, finite state machines. What we want to cover next is that there are some common operations that are common operators that are built using all these designs. And what we are particularly interested in the operations that are there in the arithmetic logic unit of a computer, of a CPU, and also maybe the memory of a CPU. Saying this, I'm not saying that other type of circuits are not important. In many digital systems, there are many other type of, or I mean, custom designed circuits that are available. But these are some common blocks or common modules that are used in many of the CPU kind of designs or ALU designs. These are the common blocks that are used. So we'll just talk about these common blocks. Let's forget about the connections. So these are some arithmetic operations you are interested in, primarily adders. And adders meaning if we work with 2's complement, adders are also subtractors. We have already talked about full adder, half adder, and the ripple carry adder. We'll discuss about the carry look ahead adder, and maybe there is another adder called the prefix adder. Besides this, there are some other operations that are important in an ALU. One is a comparator, which will allow you to compare between two numbers, whether they are greater than, less than, or equal to. And also, we would look at something called an shift register, which is used for two purposes. One is, there would be registers inside the CPU to store values as memory, to store values. And so it's not just for storage. Sometimes registers are used for other purpose also. For example, if you have an input-output operation where you have some parallel, some whole entire word stored in the registers, and you want to parallelly move them out, or read them serially and move them, store them parallelly. For example, from a keyboard. These are also used in memory as memory elements, as storage elements. And they are also used very commonly. This kind of shift registers would be used in the multiplication, because you can write down multiplication as a series of addition with changing the positional values, tens and 2 and 2 square, and you can change the value, add it, and you get a multiplier. Okay, so maybe we will not go into multipliers and division elements. Maybe you will do that in your next course. But some basic operations which are there inside, basic blocks which are there inside an ALU, we'll discuss. Okay, so let us quickly recall the adder circuits. So these are simple 1-bit adders. Like you have two inputs A and B, and you have two outputs basically. One is a sum output, which is the sum of these two bits A and B, and there is a carry output. Assuming there is no carry input available, there is a carry out and there is a sum out. If you look at the truth table, this is the simple truth table of a half adder. You have A and B, there is no carry in, so you have this carry out and the sum. You can easily write down the logic for that. Of course, a more realistic case is a full adder. This is a single bit full adder where you have two inputs A and B. I'm using this block signal because I am no longer looking into, of course, we'll expand this block and see what are the gates inside this block. But since these are very standard gates, we'll kind of talk about them as blocks and so forth. Okay, so this is a full adder. You have a carry in as well as a carry out. You have a sum and you have two inputs A and B. Now let's look at this truth table. Okay, so you have three inputs, carry in A and B, and you have two outputs, sum and carry out. If you look at the logic, let's look at the logic in slightly more detail. So this is, you look at this, the sum is nothing but the XOR of A, B, and C carrying. Sum is the XOR of A, B, and carry in. Whereas is the carry out, we'll deal with this in more detail. Carry out has two minterms, or rather not minterms, two terms. It's AB is one term, and A plus B into C in is A plus B dot C in is another term. So you can so notice one part that if we look at the carry out, so there are two cases where the carry out is 1. There are two OR cases where the carry out. One is when both A and B are 1. So this one and this one. So this is this row where the carry out is 1, and the last row where the carry out is 1. So that corresponds to this term AB. Okay, both when both inputs are 1, the carry out is 1. And the second thing you look at is that the carry out, the other two cases when it is 1, that is these two cases, that is 1 when carry in is 1 and the OR of A and B is 1. Carry in is 1 and any one of A or B is 1. Okay, so that's when carry out is 1. So these two things we can actually write in two different terms. You can think of it like this. So if this is your adder, one case is that this is your carry out and this is your carry in, and you have your A and B and your sum. Okay, so this part says that the carry out is 1. So that's the normal addition rule. It's like you take the rule. So you have 1, 1 and a carry 1. Okay, so even if the carry is 0, even if the carry in is 0, you get output 1 when A and B are 1. So that means when this holds, A and B is 1. So this is kind of irrespective of the input, it generates a carry. Even when the input irrespective of the carry in, it generates an carry out. So this part would be called a carry out generator. It generates a carry even if the carry in is 0. Now let's look at the second part, which is kind of when the carry in is 0. When the carry is 0, in which case do you, when the carry in is 1, what is the input combination for which we get carry out to be 1? Okay, so here you can see is just the A plus B. Okay, when any one of A or B is 1, or both of them are 1, and carry in is 1, then you get a carry out of 1. So this we would call a propagate, as if the 1 carry in is propagated. So this is kind of the generate is, even if the carry in is 0, a carry out would be generated because of the input when both the inputs are 1. And the second case is a propagate case. That means if the carry in is 1, it would be propagated provided any one of A or B is 1. Okay, so it's like it's a generate and propagate kind of thing. So either you generate or you propagate in each of the, either you generate or you propagate, then you get a carry out of 1. Okay, so this is just a different form in which we are looking at the carry out expression. The reason we are looking at this particular form is that these signals, this is just a visualization. This has nothing to do with implementation or anything. This is just a way of visualizing things. So we'll see that this generate and propagate step, we will propagate signals would be useful to us when we build a cascade, when we cascade the adders, 1-bit adders. When we cascade the 1-bit adders, these signals would be useful. Okay, so I think I'm not going into the circuit of a half adder or a full adder. You can just have a simple circuit for a half adder and then combine them into a full adder. Okay, you can do this. But what we want to do is that since each of these are only single bit adders, so you want to cascade them. And the simplest way to cascade so that you get a multi-bit adder. Okay, so the simplest way to cascade them is that you do like this. You have your original input carry in, then you have your inputs, and the carry generated by adding the first bit, the least significant bit, is repelled, is cascaded to the carry generated to the next bit, the second bit, and so on. So this is a simple design. As you can see that this is how we add two numbers, multi-digit numbers. This is exactly how we add two multi-digit numbers. We propagate the carry over successive places. But the problem in implementing this approach is that the delay, because you can see that every adder is kind of a set of gates. So there would be a delay. The full adder would have some delay from input to the output. And the thing is that since the next bit, the ith bit, computation would depend on the carry in from the i-1th bit, these delays would all add up. So, so suppose there is a delay of t microseconds here. Since we need C1 for this, the delay here after this would be 2t. So similarly, if we have n bits, you will have n time. If t is a delay of a single full adder circuit, and you want to add n bits, you have to wait nt amount of time before you get all the sums and the carry out. Note one thing, that if you draw out the gates that are inside each of these adder, the path with the longest delay, sometimes called the critical path, would be from carry in to carry out. So generating carry out would take the longest amount of time. Okay, whereas this sum, of course, sum depends on the carry in, but they have slightly less delay and the carry out. So the critical path is designing the carries or designing the carry outs. Okay, so what will the main problem is that we have to wait for the carry out from the previous bit, compute the sum and the carry out from the next bit. Okay, so we have to allow for this delay, and this makes the system slow. There's a significant if you have a larger number of bits, there will be a good amount of time for this rippling to happen. So is there a solution to this problem? Okay, so this would be the total amount of delay. If TFA is the delay of a full adder, you have an n bit triple carry, n times TFA would be the total delay. Okay, so now let us see. So the heart of the problem is that we have to wait for the carry out from the previous bit, previous adder. So we'll see that this is actually not required. You can kind of carry you can do a look ahead carry. You can compute the carries. So okay, so one thing, let me write down. So we have seen that carry out we have written as a generator plus a propagator, where generator is A dot B and propagator is A plus B times C. Okay, so we write carry out in this particular form. And this is for a single adder. So if we cascade the adders this way, so if we look at the ith adder, so each of these adder I can think of as having a GI signal and a PI signal. Okay, which depending on the values of AI and BI and carry in would generate the CI and PI according to these equations. Okay, so according to these equations. Sorry, I think I made a slight mistake. It is not G plus P, it is GI. So propagator is AI plus BI, whereas generator is AI times AI dot BI. So carry I plus 1 is the generator plus the propagator times the carry in for that adder. Okay, so the carry out for the ith, so each of these we would call a column. Each of these adders we would call a column. And the carry out of the ith column can be written in terms of the generator for the ith column, the propagator for the ith column, and the carry in for the ith column. Carry in for the, or rather you can think of it as the carry out of the I-1th column. Okay, so let us do this. So now let us substitute. So suppose I have 4 such adders, 4 columns of adders. 4 columns of adder. Let me not try to write down the values of this Ci. I'm not bothered about the value of sum, because sum we have already seen, we can write it in term. So if I compute Ci, I can, or rather Ci plus 1, I can use it. I know Ai plus 1, Bi plus 1. If I know Ci plus 1, I can compute the sum Si plus 1. Okay, so let me concentrate on how to compute Ci plus 1. Okay, so let me expand this. Okay, so C1, if we call these columns as A0, B0, first bit or the 0th bit, A1, B1. So I have 4 bits. I am trying to design a 4-bit carry look ahead adder. A0 to A3, B0 to B3. Okay. So the carry of the first column, C1, is G0 plus P0, C0. G0 plus P0, C0. Okay, so what I am doing is that I'm using this logic, the definition of G and P. I'm using the definition of G and P, and I'm writing down the algebraic expressions for this, as if I have some block which takes in A0, B0 and generates G0, P0, and so on. And I have this carry in here. I have this carry in here. I have this carry in here. Okay, so simple. Let me do this. So C1 is C0 plus P0, C0. C2 is G1 plus P1, C1. But C1 is G0 plus P0, C0. So if you substitute C1 with this value, you get this expansion. Similarly, C2 I have got now. C3 is G2 plus P2, C2. If I substitute C2 with this quantity, I get a similarly larger quantity. Finally, C4, the carry out of the fourth state, this carry out, if we do this substitution, again comes out to be this. Okay, so now can any of you tell me that in this expression for C4, if all these A0, B0, A1, B1, A2, B2, A3, B3 are loaded in the same, are available in the same clock cycle, how many clock cycles, or sorry, not the same clock, are available at the same time? Do we have a delay in computing C4? So look at the expansion of C4. So how fast are these G3, P3, G2, P3, P2, G1? How fast are these computed? How much delays are there in terms of the delay of a full adder? Or rather, let's take the delay of a single gate. Let's take the delay of a single gate, because G I know to be AB and P I know to be A plus B. So if I have my inputs A and B, the delay in computing G is just that of a single gate. Similarly, here also it's just that of a single gate, the AND gate and the OR gate. Okay, so from the moment I know A and B's, how much delay I need. After how much delay I know these terms? Can anybody tell? After how much delay I know these terms? Note here in this Ripple Cali adder, I would get C out after I know C in and A0, B0, A1, B1. I have to wait for NT delay till I know C out. I have to wait for this delay. Here, once I know this AB and C0, how much do you have to wait to know C4? How much I have to wait to know C4?
Sir, is it like the delay of one AND gate and the delay of one
right,
gate?
Exactly. See, because you see, each of these quantities G3, P3, G2, P2, G1, P1, and G0, P0. So there's a single AND gate and a OR gate inside. There's nothing but a single AND gate and a OR gate inside. So just it's the delay of this AND gate and OR gate, nothing else. Okay. So the delay between A3 and G3 or B3 and G3 is just one gate delay, not the n number, not n number of. So you can see, even if you cascade more number of bits, the delay would be constant. The delay is independent of the number of bits you are adding. Whereas in the ripple carry, it would be proportional to the number of bits you are adding. Okay, here it's kind of independent. It's just a constant delay for every carry out.
Sir, but in C2, like the last term is P1, P0, C0. So if we continue to let's say C31, the last term would be an end of 31 terms.
Yeah,
so,
I'm coming to that. I'm coming to that. I'm coming to that. But okay, but maybe 4-bit it's manageable. Till 4 bits, I'm coming to that. In fact, the modern VLSI, the fan-in more than 4 would be difficult to have a fan-in of more than 4, or a fan-in of more than 4 would be difficult to have. Okay, so but let's look at the circuit. What's happening? So what's the in addition to this ripple carry? In addition to this ripple, so what's the circuit inside these blocks? They are just AND gate and OR gates to compute G3, P3, G2, P2, and so on. They are just AND gates, a number of AND gates and OR gates, nothing else. Okay. Okay, AND gates and what's the circuit here? Computing C from G and P. What is the circuit we have here? So C is G plus P times C in. Okay, so the circuit you have here is kind of, you see, it's kind of, so we already have the expression for the circuit. We need more, or rather we need a, how many input OR gate here? You need a 5 input OR gate here. You need a 5 input OR gate and a 5 input AND gate also, and a 4 input AND gate here, 3 input AND gate here. Okay, so the only price we are paying to reduce this delay is to have this more number of gates. You can imagine. So C4 is this entire expression. C4 is this entire expression. Okay, I have all the signals, all these G3, P3, G2, P2, these signal lines I immediately have, immediately meaning with a single gate delay. Okay, all these lines I have, all the signal lines I have, with just a small delay after this data I have. But inside this block, we have very complicated AND and OR gates. Complicated meaning multi-input AND and OR gates. Right. So the thing is that we are paying this price. We are paying this price of additional hardware, additional gates to reduce the delays. But one thing that is for sure is that you kind of the delay is independent of the number of bits you add. So what happens actually is that it's something like this. I'll explain. Okay, so this, let us forget. Okay, delay calculation. Yeah, okay. I'll come back to that. So the delay for a single, this 4-bit is constant. Delay is constant. So now what happens if you want to scale this to more number of bits? Scale this to more number of bits. Okay, so what we have is kind of a hybrid of a ripple carry and a carry look ahead. So we have a hybrid of a ripple carry adder and a number of CLA blocks, carry look ahead blocks. Okay, so you have these CLA blocks. So the final output of the CLA blocks, final output of that is C4 here, final output of these C4 blocks are cascaded as a ripple carry adder. So what is the gain we are doing here? So you can think of it like this. So we are just cascading this, and so what's the gain we are having by this combination? Why are we combining it? And this kind of 8 number of blocks to 8 number of 4-bit CLA to get a 32-bit full adder in a ripple carry mode. Can you tell why you are doing this?
Sir, instead of n times t delay, we would have n by 4 times t delay.
Right. So if you have blocks, This is sometimes called a block carry-Lucahe adder or carry-Lucahe adder with blocks. Okay, so what we are doing, we are constrained by the number of fan-ins we can have. We are constrained by the number of fan-in we can have. So maybe we have 4 is the maximum number of fan-in we can have. So we instead of a single 32-bit ripple carry adder, we have 8 individual 4-bit carry-Lucahe adders connected in a ripple mode. So the delay would be reduced by how much? 4 times. Delay would be reduced by 4 times. That's the idea. So you can easily do the computation. So if this is the delay to generate the P and the G blocks. Okay, and T pre-G block is the delay of the block generate, so entire block. And T and OR is, so you need a finer AND OR gate. So it's the delay of the finer AND OR gate. So the final thing, as you can see, if you have K blocks, it is reduced by K with this additional. So these are individual. If you have K blocks, is the delay of the. You have a ripple, so that this part will be there. So all this we have. Okay, so there is a huge reduction. This is more useful. Okay, so there are even more faster adders. So there is something called a prefix adder. Okay, so which is something like this. It kind of, so here every block is of same size. If we look at this block ripple carry adder, every block is of same size. So what we can do instead, we can kind of compute these generate and propagate values for 1 bit, 2 bit, 4 bit, 8 bit, and so on. Okay, so until you know the carry for every column. So the idea is like this. Let me see if I have a diagram. Let me see if I have a diagram. Yeah, I think this is a better diagram. So what you do, it's kind of a logarithmic number of stages you are having. Okay, let me see how can I explain this. Okay, maybe this will help you. Okay, so what we have is that, let's say we want to generate the G and P. We want to find out the G and P for bits spanning I to J, the bits from ith to jth position. So how that is expanded is that the generate from I to G is the generate from I to K plus the propagate from I to K into the generate for up to from K minus 1 to J, 1 bit less from K minus, no, sorry, the previous block K minus 1 to J. Okay, similarly, the propagate from I to J is propagate from I to K into propagate from K minus 1 to J. Okay, so it's kind of, you block these columns of the adders, you block them and generate in a block way. So this is kind of more efficient in terms of the circuit. Is a bit complicated, this circuit. You have kind of a schematic. These are kind of block generates, and they kind of propagate. Okay, so this is even more faster. So I'll give these slides. Maybe you can look into this. I don't want to go into too much details. Okay, so there are some more circuits which are of importance in the ALU. One is a comparator circuit. This is a simple implementation of a comparator. This is a less than comparator circuit. You can also, so maybe I give this as an exercise. You can also have a very easy implementation of a less than comparator, n-bit less than comparator. So if we look into a standard ALU Okay, so one more thing I would like to say is that many of these circuits, many of these blocks, they would kind of have a control unit F, or rather a function line F. And depending on the value of F, which is often a 3-bit line, depending on the value of F, the circuits would some of the functions would be enabled. These are the common. To look at a simple ALU, these are the function. This is set left. I'm forgetting the name. Okay, so maybe one of the thing we will next study is that, and each of these are simple circuits. So what will happen is that you have blocks for each of these. You have logical and arithmetic blocks for each of these. They are all put together, and this F line, function line, would choose which one would get activated. It's not a difficult design, but the point I want to mention is that we have been talking about gates and detailed circuits. From now onwards, in your next course, where you actually design CPUs, you will treat them as blocks. You will not look into the gate level. You will treat them as blocks, which has these functions embedded in them. So the purpose of this course was to just see what is inside these blocks, and that's why we went into all this design. Okay, so this is kind of a simple circuit which looks at the F block and does all these operations. Many times using a basically you need to have a multiplexer to decide which one to have. Okay, so now let us go to the next topic, which is registers. So as you know, inside the CPU, beside this ALU, these arithmetic and logic operations, you'd have elements which would store values, which is store bit values. And that's not the only place you have. You also have them in your memory. Outside the CPU, you have them in your memory. Also, you have them in many interface devices, input-output devices. Okay, because one of the main application of these registers would be because your computation would be in parallel mode. You are computing a full word. You are doing the arithmetic operation like you have seen in the Kari-Lukayed adder. You are doing operations on an entire word, maybe 8 bits or something. But when you are reading in from a keyboard, or maybe you are communicating over a communication line, your data is transferred in a serial mode. Okay, so sometimes we would kind of read data in serial mode, but process it in parallel mode, or we would read data in parallel. We will have data in parallel mode and communicate it in serial mode. So registers often are helpful in those situations also. So in simple terms, it's as follows: a flip-flop is a 1-bit register or a 1-bit memory, whatever flip-flop you want. A register is nothing but a cascade of flip-flops or cascade of 1-bit memories. Okay, so it's a cascade of flip-flop. Okay, and then somehow these flip-flops are connected depending on what type of flip-flop you have. And then sometimes you have a circular register also. The output of the last one is connected back, sometimes, not always. Okay, so what is flip-flop? As you know, they will have some clock circuit, clock input. Usually, this clock is shared by all these flip-flops in the cascade. Usually, the clock is shared by the same clock applies to all the flip-flops in the circuit. So a register is nothing but a cascade of flip-flops. Okay. So now you can imagine that since it is of course each of these will have their own data input and output also. They will have their data input before, and output also. Besides the clock, there are often other signals like load and write and such things. Okay, so so as you can imagine, since these are flip-flops connected, cascaded in certain manner with some input coming, this can be thought of as finite state machine. So these are nothing but finite state machines. So the state assignment can depend on the values of these in the output values of this input of this cascade of flip-flops. Okay, so you can think of them as states, the value of each of the output of each of these flip-flops, and then depending on how these values change, you can think of the entire thing as a finite state machine. Now, depending on the structure of this finite state machine, or depending on the transition diagram of this finite state machine, you have different type of registers. Depending on how the finite state transition looks like, you have different type of flip-flops. So what happened? Okay. All right. So there are two ways. If you look at a flip-flop or a register, let's say, usually we'll write a register like this. Okay, so there are two modes of operation. So if we write this as say D7 to D0, this is the output. So now different modes are possible. Okay, so one of the mode is that you have two operations. So let us first talk about the operations. First operation is writing or inputting to this D7 to D0. Okay, so how to write, how to load values to this. And the second is reading from these values or outputting these values, which we call as a read. So write or an input, read or an output. Okay, so now because everything has a single clock, everything is connected to a single clock, all these flip-flops. Now this input output can be in different modes. So the serial mode is that when the input or the output, one value comes in a single clock cycle and one at a time. Okay, we'll give an example. One at a time, it comes in a single clock cycle. Whereas the parallel mode is when all the input values are input or the output values are read in a one single clock cycle. So not sequentially, in one single clock cycle. That is parallel mode. So now basically we can have four combinations. We can have serial input, serial output, serial input, serial output, serial input, parallel output, parallel input, serial output, and parallel input, parallel output. Each of these have their own application. So usually this parallel in, parallel out would be useful when you are reading value from a memory, doing some operation and loading it back to memory. Serial in, serial output is there in some, we'll see in some cases these are important. And serial in, parallel out is that maybe you are reading from a keyboard in serial manner and storing it in a register. So it's serial in, parallel out. And maybe the other way around is parallel in, serial out. So there are these different modes. Since the transition diagram would be different for each of these modes, you have different kind of logic for implementing each of these modes. Okay. One more thing, if we're looking at serial in or serial out, then this shifting from serial can happen in the following different ways. So one way is something, so you can imagine in serial in or serial out, what will or rather in serial in, what will happen is that kind of the values will come in, and one by one this will propagate. This will propagate to the flip-flops. So this propagation can happen in following three different ways. Each have their own application. One is a logical shifter. So you shift by the way, here again, these flip-flops can be a unidirectional shifting. So the shifting is always from left to right or right to left, or it can be a bidirectional shifting also. So sometimes it can move from left to right, or sometimes it can move from right to left, depending on the logic. Okay, so you can have bidirectional shift registers also. So if we talk about unidirectional shift registers, let's say left to right. So the logical shifter would fill the input will go from left to right, and the empty spaces would be filled with zeros. Empty space would be filled with zeros. So this is say for example, if this is the input and I have shifted, you can see this will be filled with zeros. And this is a left shift, this is a right shift, this is a left shift. You can see these two are filled with zeros. So can you tell me arithmetically what is the operation done by this logical left shift and right shift? Anybody? What is the arithmetic operation? Why? Where would you suppose you want to do some arithmetic operations, and which kind of operations would need a logical shifter?
Sir, integer division and multiplication by 2.
Very good, very good. Huh. We can use that inside the ALU itself. Okay, now let's look at the arithmetic shifter. It's kind of same as the logical shifter, but it will fill the empty space with the earlier most significant bit. So let's see, this is a right shift by 3 positions. Oh no, this is a right shift by 2 positions. Right shift by 2 positions. So what happens if this is a right shift by 2 positions? So this one is the MSB. So this one fills up this empty space. Okay, one fills up this empty space. Okay. So can anybody tell what is the usefulness of this arithmetic shifter? Where it would be useful of the arithmetic shifter? This is a bit complicated. Can you tell me? So in fact, we will use it for another operation in conjunction with other operations. So where do you need certain arithmetic shifting? Anybody can guess? Okay, let's see. We'll see this. When you are designing multiplier circuits, we'll need such arithmetic circuit. If you think of how we do multiplication using adders, we will. So multiplication is adders plus shifters. Okay, so now next we have rotators.
Sir, could you please explain arithmetic shifters once again?
Okay, so this is a right shift. Okay, this is a right shift, 2 positions. So what would happen is that, so what would happen in a normally right shift of 2 positions? These two would get lost. In a logical shift, these two would get lost, and the empty positions created on the left would be filled by 0. Okay, so so what I do is that instead of filling it with 0, I will take the MSB, which is 1. Oh no, MSB is 1. Oh wait. MSB is what was the original MSB? Yeah, original MSB, that is 1. And I fill that up. Okay. So this is shifted, right? 110 is shifted. 110 is shifted. This is shifted, and I fill this up with 11 because 1 is the MSB. Let's see what happens in the left shift. So this 001 is shifted. But why do we have a 00 here? Why do we have a 00 here? So only thing is that instead of filling up the empty space with 00, I would fill up the empty space with the earlier MSB. I'd fill it up with earlier MSB. Right. So is this example correct? Is this example correct? Wait a minute. I'm not filling with 00, I'm filling up with the MSB. So this is fine. This right shift is fine. I am trying to figure out what is happening in the left shift. Okay, whereas the earlier MSB was 110. Just a minute. Okay, all right. All right. So what happens is that, so see, this you are shifting. So 110 you are shifting. What happens is the MSB which is there, that is filled up, that is copied. So this would be just copied. Okay. So similarly 001 you are filling up. The 0 is the MSB. That is what you are copying. So the MSB just fills up. So you are shifting whatever you are shifting. The MSB of that part would be copied to the empty spaces. Okay, maybe I'll check up. Maybe I messed up the definition. All right, but let's look at the rotate. Rotate is kind of circular. Rotate is kind of circular. So if you rotate right 2 positions, if you rotate right 2 positions, you see these two would come back here. These two would come back here. Okay. So can you tell me what should be the procedure of implementing these kind of shifters? How would I design? So if I'm given these shifters, what would be my design? How do you go about designing this? I don't want to go into the exact connection upgrades.
In the
Yes.
leftmost flip-flop, we can have a loop, self-loop, so that it gets copied. Okay.
It gets copied, right? Achha, by the way, one thing before that, one simple thing let us do. So I think the serial in, serial out shift register, that's pretty simple. All you need to do is to have your flip-flops, maybe D flip-flops. All you need to do is to just cascade them. And have a common clock. Okay, you can imagine if you tap these outputs, each of these outputs, and if you have a serial in, it will just propagate. The input would just propagate along this. So if you have 4 flip-flops, you have to wait for 4 cycles till the correct value is loaded in all the flip-flops because it's serial in. So that's by nature, because your data is arriving 1 in each clock cycle. So you have to wait for clock cycle after you can parallelly read out all the values. Okay. So can you tell me what will happen for, let's say, a parallel in, parallel out? How do you implement a parallel in, parallel out shift register? What kind of extra line or what kind of signals would you require for a parallel in, parallel out?
Sir, clock and 4 input and 4 separate outputs.
Clock, 4 input, 4 separate output. Very good. What would you need for a parallel in, serial out? What do you need for
So
a parallel
clock,
in?
4 inputs and 1 serial output.
Yeah, but how do you get the serial output? Because serial output means it would look like a train of data. So the entire data should not come in a, because you can only say use serial data. So you have to get them one by one. You have loaded all the data parallelly, but how do you serially read them out? Say suppose I have parallelly loaded 1 0 0 1. So if I need a serial out, I would have 1, then 0 0, then 1, like this. I need some output, serial output like this. So how would I get that output? What kind of additional logic or line would I need? Control line do I need? Okay, so usually what is done, you can easily design the logic. I'm not designing the logic. You have another line which is called write shift. In fact, there's another line called write bar shift. So this is one additional line you have to this entire thing. So when this write shift is 0, when this write shift line is 0, write shift control is 0, then the value is written. Parallelly the values are written. And when this write shift line is 1, the values are shifted. And so now if you can use this write shift line, then the final output of the final flip-flop, that would give you a serial output. And how do you transition? How do you propagate this? You have to keep the shift on. So you have to make the write on for one cycle, one clock cycle. You have to make the write on where you can write. Then if you have k number of flip-flops, you have to keep the shift on for k cycles. Okay, so it would be write for one cycle and then shift for maybe k number of cycles. So write for one cycle and shift for k cycles. So this would give you a parallel in, serial out, because it will keep on shifting, and if you look at the output of the final flip-flop, you'll get the serial out. Okay, so what would happen? What would be the structure of the write shift signal for serial in, parallel out? Serial in, parallel out. So it would be the other way around. You have to keep the shift on for k number of things till you get all the serial in, then have the write bar for one cycle when you do the parallel out. It would be the complement. Okay. If it is parallel in, parallel out, you kind of need a latch. So there are two situations possible. One is write, and then you latch it for one cycle, and then you read. And serial in, serial out, this shift would be on always. It would always be on. You would serially shift in and shift out. I am not going into the logic for this write shift line. That would depend on what type of flip-flop you are using, but it's not very difficult to implement. It's not very difficult to implement. Okay, all right. Also, it not only depends on what type of flip-flop you are using, it also depends on what kind of shifting you want to do. If you want to logically shift, then the logic for this write shift line would be something. If you want to do a rotation, for example, this write shift line would be something else. So these designs I am not doing because they are simple in the sense all you need to do is to, all of them will just use a AND or and a NOT gate, nothing else. So you can just write down the truth table. It's easy. You can write down the transition diagram and the truth table and realize those circuits. Okay, but from now on, let's treat them as blocks, which will combine to build more complicated circuits. Okay, I'm not going into this anymore. You can have such shifter. There are more complex shifter designs like barrel shifters. So these are like one single circuit in different modes of operation can function as a CISO or a PISO or a SIPO or a PIPO circuit, depending on also you can change the direction of the shift. It's a very general circuit. It's kind of motivated by in the cellars, wine cellars, how do you move the wine barrels? So they are moved in a very efficient way. It's motivated from that. I don't think we have time to talk about this barrel shifter circuit, but it's a very nice circuit. You can look at the circuit. Okay, so I'm not going into this. You can use all these shifters to multiply and divide and all these things. I'm not going into them. So maybe with this I'll stop. With this I'll stop. Okay, I think that's it. We can stop for today. One announcement. Next, so our last class is next Wednesday. So do you want the test next Wednesday or next to next Wednesday? We have to take one more test covering the rest of the elements, rest of the topics. Anyway, we'll decide that. Okay, so bye for now.